Honk.
Honk.
Honk. If you have not yet joined the Science Track Discord, you should join the Science Track Discord.
And you'll understand then why we honk at each other. Speaking of which, so after the track, let's get this over with, we have Science Track ribbons.
Come get one.
We have normal purple with sciencey stuff. And we have goose.
Yeah.
You can guess which one we prefer. Honk.
What about the charity?
The charity.
The charity bucket?
The charity bucket. Yes, we are collecting money for Big Brothers, Big Sisters, Atlanta.
Yep, that's correct.
So please. Oh, there we go. Thank you.
Yes.
Dragon Con is matching up to $100,000. And as Stephen said earlier, we would really like to make Dragon Con cut a very big check. So please drop money in the bucket.
What else do we usually cover in the beginning and or end while we're rushing to finish? So you're getting all of this now because our moderator has run off to get an adapter, so we're vamping
social
for a bit.
media, where to find us?
Yeah.
Yes.
I was also going to say the app. If you enjoyed this panel or if you totally hate us, whatever, it's fine. Make sure you rate this panel on the app. They do actually look at the comments.
It encourages them to give us another panel next year where we can be even more goofy.
Speaking of other panels that will be even more goofy, if you haven't had enough Science Track after this, you should head over to, I forget what ballroom after this, for Fight, Flight, or Mate. Grand East should be a good time.
So for Fight,
Flight,
Flight,
or Mate.
The three Fs.
There may
and I understand that there may be scientists doing mating dances.
I can neither confirm nor deny that information.
I actually don't know who's doing that this year, since our usual.
Emily.
Don't spoil it.
No, I mean who's on panel, but
No. I mean who's doing the dances?
I haven't heard.
Because our good friend Ryan could not make it this year, unfortunately.
Bless him.
And for
He's
those
fine.
of you
He's in Toronto.
who like it a little more fictional, also at 10 p.m. up in Hyatt Embassy AB, there is the First Contact Improv, where we will be making authors dance, interpretive dance for our aliens who don't speak our language.
That's brilliant.
Excellent.
I love it. Hey!
There she is.
Woo! The chapter is here.
Okay.
Aw. We're the only one. Oh, well.
You don't have 9 volt.
What?
We have a
Yeah, also, so I don't think they might not have gotten over yet, but masks are required in the chat room, please. If you have a drink, you can hold it down quickly and take a sip. Put your mask back up. It needs to go over both your nose and your mouth. And we will not start the panel until everybody is helping us follow that rule. So, thank you for that.
Hi.
You want to take over now?
Yeah. Hi, everybody.
Hello.
I'm so sorry about the delay. That's entirely my fault. Sometimes you forget the converter you need, but now we are all here and we're all together again, which is wonderful.
Woo!
So let's fight! So, one point of order before we get started. Matt already mentioned the mask rule. Also, if you haven't heard, this year we are collecting for Big Brothers, Big Sisters of Atlanta. So please come and give your donation. Otherwise, I'm going to
communicate things multiple times. It's fine.
Can everyone see EM Spectrum Fight on the 2 screens?
Nope.
No.
Oh, dear.
Well done!
I told you I can do mine with interpretive dance. Seriously.
I have had to do interpretive dance of my dissertation.
Okay, they were off.
The ONOFF system was.
Wow. Oh my god, it's just like my class.
Never trust a scientist with anything technical. Okay.
I resemble that remark.
I do biology and I knew it. Wait.
To be fair,
It would not work with my laptop.
I tested this laptop in this room with this light.
This is literally how my class goes once or twice a semester. It's just like
Same.
I completely gave up and used a whiteboard. Honestly, if they gave us a whiteboard, we wouldn't need slides.
If we all did interpretive dance, we also wouldn't need slides.
That is true.
I brought props.
Uh-oh.
Watch out for falling lightsabers.
Lightsaber fail. There's a lightsaber down in aisle 3.
That is not doing what I told it to do.
That's all right. We can roll with it.
Do you want to start with intros while
Yeah.
we figure it out?
Yeah,
Yeah.
why don't each of you introduce yourselves, tell us a little bit about what you work on while I desperately try to get this display to work.
Awesome.
Hi, I'm Rob Hampson. I am a physiologist, pharmacologist who happens to work in neurology, and you'll gather all of that from my favored wavelength and frequency. But I also do a lot of work here with science track, space track, sci-fi literature track, and Apocalypse Rising.
Hi, I'm Nicole Gugliucci. I am a professor. I am on the internet as Noisy Astronomer. My background is in radio astronomy, so that's pretty obvious why I'm here. I also do astronomy. Shush. I also do a lot more education research, astronomy education, anything that involves communicating science and celebrating science with people is my jam.
Who is it? I'm Topher Hunter. I am a PhD biomedical engineer. I have spent most of my career in orthopedics, diagnostic medicine, and microbiology, infection control. So I've kind of played with lots of different things, but basically all in the medicine space.
And I'm Jennifer Greco. I am also an astronomer, but I live over in the infrared. I study low-mass stars and exoplanets. I'm now an astronomy postdoc at Uppsala University in Sweden.
Woo! Woo woo!
The mirror just doesn't
And
work.
we see the slides.
Fine.
Woo!
No, you don't. The mirror's not working.
Can you
The mirror is
extend
not
and do
working.
the,
Yeah.
No, that's fake. I promise you that's fake.
Okay.
So we're in the mirror universe. Everyone's got beards.
So now it's real, but we can't see it.
Cool.
That's all right. We can win. No,
Yeah,
That's okay.
We can't see the slides.
it's like PowerPoint karaoke. It's fine.
I mean,
What if we...
You could stand here and then
I was going to say, what if we use the cordless mic and just...
the cordless mic has no battery.
Excellent. What if we just yell really loud? I don't know.
What if we tell you what the slide is?
I,
I think
am I the only one who has their own slides on their phone?
here's what we're
Yes.
gonna do.
Yes.
Guys, people, please. What we're gonna do is one by one, you're gonna come over here. If you stand there, you can get this mic. Don't cross the speaker. You should be able to see your slides and tell me when to advance.
Can I sit here and just use mine and tell you when to advance?
That works.
Okay. 'Cause I'm lazy. I don't want to get up.
So now I need to very carefully get that into presentation mode. So audience, I need you to help me because I can't see my mouse. I need to get it to the upper right and hit present. So can you tell me where I need to go?
Best panel ever.
There's no F5, it's a Chromebook. So after many, many types of shenanigans, I would like to welcome you all to EM Spectrum 5!
You be okay over there?
For our first contestant, we have Dr. Greco. Come on down.
You guys are much more helpful than my students when I try and get them to do that.
All right, where am I
In
supposed...
class.
Okay. I'm going to stand here and not move so no one goes deaf. All right, unsurprisingly, I am here to rep the infrared. Next slide. Advance. All right, there we go. So, what is the infrared? Well, first of all, you can't see it with your eyes, so the infrared is outside the visible. Infrared literally translates to below the red. You can see it, I don't know why I'm pointing at the monitor like all of you can see what I'm doing. So, you can see where it says infrared. It runs from about 800 nanometers to about a few hundred microns, and it's split into 3 wavelength ranges: the near infrared, the mid infrared, and the far infrared. I live in the near infrared. It's where I do most of my research. Basically, what I want you to know is different wavelengths let you see different temperatures because, next slide, what we're looking at with the infrared is basically light emitted by heat. So you can't see it, but every single person in this room is emitting in the infrared right now. And if I looked at you all with a thermal camera, I would probably see, well, not exactly that because you're all human-shaped, but work with me here. So you can see, basically, infrared light is sensitive to temperature. So things that are darker are colder, things that are brighter are hotter. Next slide. So now I'm going to tell you about some of the interesting things that we can do with the infrared that makes it basically the most awesome part of the spectrum. And the first one...
Ow! They were empty, it's fine!
Now there's no slides. All right, so you can see 2 pictures of a teapot. The one on the left is the visible picture, can't see what's in the teapot. If you look at it in the infrared, you can see not only that there's water in it, but whether it's hot water or cold water. Why do you care about that? Well, you're all wearing masks right now. If you want to do, say, facial recognition through a mask, you need a camera that can see through your mask. Okay, another thing this lets us do is you can see things like blood circulation in the human body. So looking at those 2 feet in the visible, they'd look the same, but in the infrared, you can see which one has better blood flow and where the bad one has bad blood flow. But I'm an astronomer, so I'm going to spend the last bit of my time talking about why this is awesome for astronomical reasons. And the first one is that it lets us see through gas and dust. And I don't know if you know this, but space is full of gas and dust. And we have a lot of what we call nebulas, which is what that really, really pretty picture on the left is. And they look really nice, but I can't see what's in it. And looking at it in the infrared lets me look past all the gas and dust to see, for example, the structure of all the stars in it, which lets me learn about the physics of what's going on, and also things like where stars are forming. So we're going to start with the 2 images on the left, which is 2 images of Orion. You can see Orion in the visible light. You've maybe seen it before. You can see on the right all the really, really bright hot spots in Orion. That's where all the stars are forming. And if I want to learn about where in a galaxy stars are being born, I can do that with the 2 images on the right. I can see where the stars in that galaxy are being born. Infrared lets us do that. It lets us track star formation. It also lets us see objects that aren't visible to the human eye. So my thesis was on these cold, low-mass stars called brown dwarf stars, which are so cold they don't emit visible light. If you look for them in the visible, you get that image on the left. Notice how the circle in the middle is empty? Now, if you look on the right in the infrared, you can see that all of a sudden the brown dwarf has appeared. Interesting bit of trivia, the 3rd and 4th closest objects to our sun are both brown dwarfs, both unable to be found without looking in the infrared. Also planets, I mentioned I do exoplanets. This is not an exoplanet, this is Jupiter. But if you look at it in the infrared, you can learn a lot about, for example, the physics of its clouds. So those really bright hot spots, you're looking deep in the atmosphere and seeing what's going on deep and hot in the atmosphere, and then you can also see the clouds on the surface. So you can learn a lot by looking at planets in the infrared as well. And last, what I spend basically my entire life doing is spectroscopy. So think about spectroscopy like you make rainbows with a prism, right? You take white light, you break it up by color. If I do that with starlight using a telescope, I get something that looks like this. And I don't expect all the non-astronomers in the room to know what that means. What I want you to notice is that on it we've labeled a bunch of different atoms and molecules. So essentially what near-infrared spectra, or infrared spectra in general, let us do is it lets us break the light up by color and see what atmospheres are made of. And if we're looking for things like habitable exoplanets, this is how we do it. Thank you.
Phenomenal! So next, we have Dr. Hunter.
Cool. Thank you. All right, so yeah, sure. Okay, hey, look at that. So, as I mentioned, I'm in the medical space, and in diagnostics, we actually use the entire spectrum from
Cheating.
Cheating.
look, just because you can only use part of it. But seriously, for anything from radio waves in MRI, which I'll talk about in a second, to into X-rays, the visible spectrum, the UV spectrum, up to microwaves for radar imaging of cancerous tumors, up to higher energy things like SPECT and PET and CT exams and all these things. Literally, the entirety of the EM spectrum is utilized. So it's really cool, and it was really hard for me to pick something. And actually, when I first picked this, I was at one end of the spectrum, and now when I finally decided what I was going to talk about, I decided to do it the other end. So, what the important thing, if we can slip to the next, what? Honk! Honk! That does not look like, okay.
Ignore this.
Wow!
Yes, it's messed up. Just go.
That's cool. Okay. So, what I wanted to talk about briefly is MRI, magnetic resonance imaging. But first off, the original name for MRI is actually nuclear magnetic resonance imaging. They took the nuclear term out because they thought it would scare the dickens out of the patients. So, but the cool thing about it is that we always talk about the EM spectrum, we talk about the E part of the spectrum, but if you rotate 90 degrees through space, essentially, you get to the magnetic part. And that's where things really start to get cool from an MRI perspective. So, what happens? Okay, now this is going to be the fun part. What happens is hydrogen atoms can essentially be thought of as little spinning tops. So they're sitting there pirouetting, and I can't do it or I'll trip myself on the cable, but they're sitting there spinning around. And just wait, it gets better.
Uh-oh.
If you apply a really strong magnetic field, like a Tesla, which is many, many orders of magnitude stronger than the Earth's magnetic field, you can actually snap those little spinning tops onto their side to align with the magnetic field. So our lovely dancers would be lying on the floor, spinning on the floor. They are so good.
We tried.
Now, what happens next is when we turn the magnetic field off, they will slowly process back into their normal random state. So, turns out when you move a little tiny magnet inside an electromagnetic field, it emits a radio pulse. So for the first time when it got snapped down, and then the slow time when it relaxes back, those are referred to as the T1 and the T2, which are way more complex than I want to bother getting into. I don't even understand it, I just use it. They emit a radio frequency pulse. So if you put a little radio antenna over the leg or the arm or the brain or whatever it is that we're trying to image, you can now detect that little pulse, that little bit of the hydrogen atom as it processes, and it's going, hey, I'm here. And with T1 and T2 and then a whole bunch of really complex things, like we can inject paramagnetic solutions into the body, and then we look at where those go. Everything that we do with MRI, what we're doing is we're detecting the presence of hydrogen, which is basically detecting the presence of water. And the more mobile that water is, the more we get, the more signal we get. So depending on the T1 and T2, we can get images of all these different parts of the body that are completely unimageable with things like X-ray or ultrasound. And we can get these amazing images of what's going on inside of the body without using an ionizing radiation. So I can give you as many MRIs as I can possibly cram you through in your lifetime, never going to do any harm, as opposed to there's a certain limit of the number of X-rays or CTs I can put you through. but we can give you MRIs until the end of creation. And we get all this amazing diagnostic capability. So it all comes together. So what's my favorite part of the EM spectrum is actually rotate it through. It's the M part of the EM spectrum. Okay.
Okay, next up is, oh my goodness, I should have practiced this.
No, noisy astronomers.
Is Noisy Astronomer. Here you go, and the kid,
Tap that to get to your first slide. Space?
yep, space. Keep on with space.
Oh, there we go. This is my very imaginative title, you guys. Actually, for a little context, this started as an actual argument involving me and Topher on GroupMe. So I find it interesting that, hang on, I gotta. I know. It's making the mic hard.
It was actually an argument a year ago tomorrow.
Yes, he found the original messages as we were at Virtual Dragon Con. So I find it interesting that we kind of ended up in the same place wavelength-wise. Being a radio astronomer, the radio part of the spectrum is my favorite. And when I say radio, I am talking about from wavelengths of tens of meters and bigger all the way to millimeter and submillimeter. Y'all are familiar with radio waves because you, at some point, have listened to the radio. And I love to do this little demo with my students that involves using an actual AM/FM radio, which is really hard to find these days, and playing music and putting a wire mesh over it and seeing it cut the signal, but then playing a song from that I've downloaded on my phone. And putting the wire mesh over it and seeing it's not blocking the sound, it's blocking the light from the radio waves. Radio waves are, in general, the most very useful part of the spectrum because we have radio waves that are used for communications and Wi-Fi and all that fun stuff. As an astronomer, this stuff is kind of terrible from one perspective because it makes it really hard to see the faint radio waves from space. But as a human who likes communicating with other humans, I think that makes it a pretty useful part of the spectrum. Another way that you can communicate with radio waves is across the entire Earth. You have some waves of a long enough wavelength that they will actually curve and you can kind of like bounce them off of the atmosphere itself and communicate with other parts of the planet. Story about why ham radio is still so important. I had a friend who was a postdoctoral researcher at Arecibo when it got hit by Hurricane Maria. And we lost contact with them, and it was a ham radio operator who was the first to make contact with them and tell us on the mainland that she was okay. Everyone was okay at the observatory. They were alive. They were like one of the few places with water. They were providing the community. So ham radio, though an art I think with fewer and fewer practitioners, is still super cool, super important. It's another reason. Yes, this microwaves. This is another reason that radio waves are so important and my favorite part of the spectrum. This is my second favorite way of cooking. My first favorite is dump things in crock pot, but this is my second favorite way of cooking. What I like about radio waves is they are accessible with technology that you can put together yourself. One of the second person ever to do radio astronomy was a citizen scientist. He was an engineer called Greco. He built this dish in his backyard, or like an empty lot, I think, that was next to his house, and mapped the galaxy in his spare time. This was before astronomers were paying any attention to the fact that radio waves had been discovered coming from the galaxy, and he mapped the galaxy and made the editors. I think it was the Astronomical Journal, actually had to come to his house and inspect it to be like, really? And ended up creating an entire new field of astronomy. I love it because it's accessible to my students. My big thing is astroeducation. It is so easy to grab satellite TV dishes off of Craigslist, or literally, like, what was it, 2-3 weeks ago? I was driving back home from the grocery store, and I saw this big big Dish Network dish at the side, at someone's curb, and I had to stop and put down my seats and put it in my car because you can make a really simple radio telescope out of that. And hand it to a kid. So this is two of my college students teaching this to one of the high school kids in town, detecting the sun on a cloudy day with a tiny, tiny radio telescope. I don't know how well you can see that, but the radio sky is quite gorgeous. It looks like a field of stars like you would see in the visible. However, each of those is a galaxy. It's coming from the region around a supermassive black hole in a distant galaxy. Each one of those things that looks like stars. I like this one because it moves, but it also shows you just how easy it is to pick up radio waves and how fun they can be. You really just need a wire. We currently have a radio telescope at my tiny campus, which is literally a copper wire strung out between PVC poles that can detect solar bursts from Jupiter and the sun. Of course, you could get more sophisticated. You can put a bunch of these radio telescopes together, use some fancy math and Fourier transforms to get beautiful images of things like the event horizon of a black hole. So black holes, of course, being one of my favorite things. It may not look like much, but I literally screamed with delight when I saw this, when it was announced. And then other things that you can see in the radio and astronomy. This is a forming solar system. This was seen with the ALMA telescope, which is a sub-millimeter telescope high in the mountains of Chile. I went there once. It's at 16,000 feet. As you can see, I get very excited and very jumpy. Doing that at 16,000 feet is a bad idea. But it is very exciting, and you can see baby solar systems forming. Is that my last one? Oh, no. One more, real quick. For those who think that the radio part of the spectrum is too low energy to be interesting, I submit to you that you can not vaporize, not just vaporize, but sublimate a chicken. From solid to liquid with radio waves. Modeling that, doing the math, using the beloved Arecibo radar, of course, rest in peace. It only takes 10 nanoseconds, so 10 to the negative 9 seconds to sublimate, turn a chicken into vapor. Now, a story I was told as a baby radio astronomer was that this was actually done at Arecibo. And I wasn't sure I believed it until I actually met someone, a friend of my department chair, who witnessed it. What? It was literally there, and then not. It was breathtaking. There was a biped. I don't know if chickens are actually bipeds. And then not. So he actually witnessed this event. It was like they had chicken and then chicken was gone. My students felt so bad for the vaporized chicken that they adopted it. What? I don't know, and I didn't ask. Asked if it was alive. But yeah, radio astronomers can be terrible, apparently. But my students did adopt the sublimated chicken, which is now the mascot of the Society of Physics students at my college.
Thank you.
I couldn't believe it was real.
Okay, and we test, check. I don't know. You handed it to me. Check. Oh, wow. Okay. Great. And now we have our last part of the spectrum with
Dr. Robert Hampson.
Dr. Robert Hampson.
All right, I am going to talk to you about the part of the spectrum that is the most important to you. These are all very, very important wavelengths and frequencies. But the one I'm talking about here is what makes you, you. In the brain, we have don't cross the streams. Right. So in the brain, we have a number of different oscillator frequencies that are active. These, when you have one cell fire, you get a little pop, 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 pop. One little neuron puttering along its way, encoding information that is very important to us, whether it's the movement of an arm or the feel of a breeze going past your skin or the blink of an eye. Any of these things are going to activate the neurons in your brain. When you have a lot of neurons active, you get what we call a field potential, and that is the sum of the electrical or electromagnetic energy from all of those neurons at a time. When you have an entire brain with billions of cells, of neurons, that are active, you start to see oscillators. So my favorite part of the spectrum is between 4 and 6 hertz. That is the slowest frequency you've heard of today. The wavelength is between 50 and 75 million meters.
What?
That is 1/5 of the distance to the moon. One wave,
Awesome.
one cycle, one of those 4 times per second. In a quarter of a second, light will go 1/5 of the distance to the moon. And what you see with the wavelength, about 300, 30,000, 45,000 miles. And so we have the 4 to 6 hertz frequency. Okay, why is this so important? Well, brain activity is broken into oscillation bands. We have the delta band, which is about half a hertz. So once every 2 seconds, you get one complete cycle of the delta. Delta is very important to sleep. When you are in deep sleep, your brain rhythms, your brain activity is dominated by delta. And that's the one that gives you restoration and helps your brain reset after a nice busy day of all of these panels here at Dragon Con. And it's that deep sleep that you're not going to be getting until about 5 a.m., right? Yeah, right.
On Tuesday.
So,
On Tuesday.
on Tuesday, yes, there you go. Next fastest rhythm is theta. And you get a number of different reports. We have up here, I've mentioned it as 4 to 6 hertz. There's another, the broader range is about 3.5 to 7 hertz. So that's theta, and I'm going to talk a little bit more about theta in just a minute. Then we have the alpha band. Everybody hear about alpha rhythms in the brain? The alpha rhythm is the quiet meditative activity. That's what we call the default mode network of the brain. The default mode is you're sitting, you're breathing, your eyes may or may not be open. You're not sleeping, but you're just sitting quiet. That's the meditation mode. Next, we have the beta frequency. Beta frequency is running, so alpha is about 7 to 11 hertz. Beta is 13 to about 30 hertz. And what we actually find is that brain activity in the beta band is very desynchronized. It's not synchronous. It's not a lot of cells active at the same time. They're a lot faster. Most of what's going on when you are active, when your brain is active, if you're doing mental exercise of some sort, if you're thinking about something, if you're cogitating, if you are speaking, if you're moving, if you are doing, then one of the things that you will see is a lot of beta band activity. And it's one of the broadest bands that's up there on our list. Then we have the gamma band. The gamma band runs from about, well, on that one, we're talking about 30 to 140 hertz. Now, that is the frequency of cells that are active in the cortex of the brain when they're processing specific information, visual information, auditory information, touch information. It's very localized, very fast. But theta turns out to be the most important of those oscillators because it is what we call the heartbeat of memory. Theta oscillation is what coordinates a number of different brain areas, particularly in what we call the limbic system or the Pepes memory circuit. The Pepes memory circuit involves the nucleus basalis of Meinert, the fornix, the septum, the medial septum, the hippocampus, my favorite, which does not refer to Berkeley, but the hippocampus is a structure that's about an inch inward from this point right here on our temple. And it is one of the major structures in creating new memory. We also see extension from the hippocampus into the cortex, into prefrontal cortex, into entorhinal cortex, which is here, and other parts of the brain. One of the things we know that is very, very important, when memory is working well, all of those brain areas are synchronized to theta. When memory is not working well, the theta rhythms in the various brain areas are either weak or desynchronized. Most famous memory degenerative disease is Alzheimer's disease. Alzheimer's disease is primarily a disease of the memory circuits. One of the ways we know about Alzheimer's disease predates actually the studies of Alois Alzheimer. And we talk about a very famous patient called HM. And HM had surgery that removed portions of his hippocampus, and he could not make new memories. Alzheimer noticed that in patients who were showing difficulty with memory, that they were seeing damage to the hippocampus. And when you don't have the hippocampus, you get a lot of desynchronization and weakness in the theta rhythm. So one of the things we see is that in normal human functioning of the mind, of the brain, of the memory, we see strong theta rhythms, synchronized theta rhythms. When we start to see the degradation that comes with Alzheimer's disease, then a lot of that synchrony and a lot of that strong rhythm disappears, goes away. But if we had a way to improve that, then we could restore the theta, then we could actually, if not reverse, at least slow down the progress of theta. And actually there are, of Alzheimer's disease by restoring theta. And that's actually one of the studies that is that's undergoing right now at Wake Forest in my laboratory, is how can we reverse the memory deficits that we see, because what is it that memory really does for us? Memory is tied up with our sense of self. If we don't have our memory, we don't know who we are. At the core of human memory is the theta rhythm. So I would argue that the most important frequency and wavelength of all of these EM is the one that makes us who we are. And that's the theta rhythm.
So, now we've seen all the presentations, so let's let things get a little bit spicy. We are going to go down the line, and I'm going to ask each of you to pose a gentle or not so gentle question to one of your colleagues. So Jen, let's begin. Who do you want to grill?
Why do I have to start?
That chicken?
Yeah, I'm still traumatized by the radio chicken.
Radio astronomers can be terrible. I apologize.
If you don't want to start, we can skip and come back.
Yeah, why don't we skip and come back?
Topher.
Okay, I'm gonna tie into your chicken question or story. There's a possibly apocryphal story. I don't know. The Viking landers were the first two landers that humans placed on Mars. They were massive science experiments, very cool, lots of cool engineering. One of them, at one point, eventually, and I can't remember if it's one or two, basically accidentally was told to turn its receiver dish towards the ground. So we lost contact with the lander. The story goes that at one point, the mission control team gained access to the Arecibo network and tried to basically transmit a pulse back to Mars, telling the lander, look up. And so they sent, the idea being if they could send enough energy, some of it might bounce off the soil of Mars and then up into the antenna, and they might just get enough information or enough signal into the antenna to get it to wake up and look up. And the story goes that it didn't work, of course. And the story goes that, well, if there wasn't life on Mars before, it's gone now. So, comment.
I have heard that same story, apocryphal or true, I'm not sure. By the time it's gotten to Mars, I suspect it will have spread out enough. The chicken was right near the actual transmitter feed, whereas Mars is a lot further away, so I think it would have spread a bit.
So you're saying that your amazing chicken cooking technique doesn't really work because you need to be close.
I concede this point.
Well, now it's your turn to fire on back if you want.
Actually, I have a question for Robert because I've been having trouble sleeping lately. The semester started, trying to get ready for Dragon Con. My brain's like, blah, 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 blah. That's what it sounds like in there. And I discovered there's some really nice meditations to help me sleep, and it's usually somebody talking you through like muscle relaxation techniques, which is cool. But scrolling through the app, I'm finding these things called binaural beats that are supposed to train your brain to sync up with delta waves and sleep better, or theta waves to remember things better. I like the pretty sounds. Is there any science going on there?
Well, it's an interesting point because there's a little bit of what happens is our brains will adopt a rhythm that they can see and hear. So here's time for apocryphal stories. One of the things that we do in a neurophysiology laboratory is to put electrodes, put wires into the brains of rats, mice, sometimes monkeys, and sometimes humans. And when we're recording, we can see the activity. We can hear the activity. If we're recording from single neurons, they go depending on what type of activity, where we are in the brain. There is one thing that we cannot ever do. Let the subject hear their own brain activity, because it will bias it, it will change it. And sometimes what we see and has been reported as apocryphal is instances where seizures have been caused because when you're recording from a particular part of the brain that could be involved in a seizure, and your little rat is listening to their own brain activity that goes bop 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 and boom, now you've got a seizure.
Like when you cross the speaker line with the microphone.
There you go.
Exactly. Guilty as charged.
Brains are weird.
So
I'm going to
there
sleep real well tonight thinking about that. Thank you.
So there is some element of, yes, you want to train. Yes, you can listen to something really, really relaxing. What it probably does has more to do with put you in the meditative state, because guess what? The actual act of listening to the beats is activating your auditory cortex, which is running a whole lot faster. That's beta activity, which is a whole lot faster than the alpha rhythm that you are trying to produce.
Oh, interesting.
Okay.
So do you have a question for
Right,
one of
I have
our
a question
colleagues?
for Topher about when we're talking about all of the imaging, the one thing I didn't hear about was magnetoencephalography. Ooh, where we actually are recording the magnetic activity or magnetic signatures of the activity in the brain.
It's. I mean, I'll admit it's not really an area I've spent much time in. So if you know more than I do, please.
Are you
This-
bolstering
I wanna
his
know this.
argument with stuff he
Please
doesn't
keep going.
know? That's
Please.
No,
rude.
actually, shame on you. Shame.
Look, okay, wait a minute. I'm in orthopedics. I deal with the hard stuff. Maybe the muscle and tendon stuff. The brain is squishy,
So
you're
are
not wrong.
chickens.
and
You're
it
not
scares the
wrong.
hell out of me.
You're not wrong.
Jen, did you come up with a question?
So none of us picked on Jen.
Yeah.
Yes.
I'm not going to pick on myself and do my own argument. I want to go back to the radio astronomy cooking and not the chicken, but like other methods of cooking. I have heard that if you have a microwave in a radio observatory, it can mess with the telescope, and the telescope's picking up microwave signals. Can you comment on
Are
this?
you a plant?
So
No?
no, it's legit. So I did a fair amount of my graduate school work in Green Bank, West Virginia, the site of the National Radio. Oh, I'm seeing claps because it's so great.
Yes.
The National Radio Astronomy Observatory, which is in the National Radio Quiet Zone, where they actually have control over what can be transmitted, and especially right on site and in the town. So if you miss dinner, if you're out working in the field and you miss dinner in the cafeteria, and if you're lucky and the cafeteria ladies like you, which we managed to pull off, and they're lovely and amazing, they will save food for you. But how do you heat it up? You can get special access to one microwave on site that is inside of a giant metal, locked box. So yes, particularly if you're only using one radio telescope at a time, any human-made radio signals are an issue. And so when you show up, if you show up to Green Bank for a tour, they're going to be like, turn your cell phones off. I mean, first, it's useless. You're not getting the signal. But so turn it off.
No radio towers. Yeah.
No, there's no. There's one tiny little cell phone tower at a ski resort, but they've directed most of it away. You can't use. I mean, okay, so this has been a while. You can't use digital cameras. I don't even think people have this anymore. But you can't. They actually sell disposable cameras in the gift shop specifically so that you can take your pictures. Yes, it is true that microwaves are an issue. So do not drive your microwave through West Virginia, at least. Some other measures that they take, everything has to be tested in these special anechoic chambers. If you've ever seen these before, they have these spiky foam walls. But they test the electronics that we were putting out for our radio telescope, so it wouldn't interfere with the other radio telescopes. So it's really an interesting place to be when you want to build a sophisticated piece of equipment to study the radio waves from the universe, and your sophisticated piece of equipment gives off radio waves. It's a little bit tricky, but it's a lot of fun.
I just want to point out that I can microwave my dinner when I'm observing in the infrared.
Oh.
But our cafeteria is better.
That's not very hard because we didn't have a cafeteria.
So I think I've seen a bit of audience interest, so I'll leave a bit of time for questions, and then we will get on to the voting.
Dun, dun, dun.
Oh my.
Oh no.
Yeah. Oh no.
Hi. So we know that one spectrum has distance issues and another might cause seizures, but only if they're listening. Which part of this band is best for making the best death ray?
Ask the chicken.
So that that actually goes to the other part of the spectrum that I was tempted to talk about, which is gamma rays.
Yeah.
Trying to be real quick, there's gamma rays are incredibly high energy transmissions, and starting in the 60s and then really in the 2000s, we first developed technology to do what's called stereotactic radiation therapy. So we can generate a beam of collimated gamma energy, and so one little beam by itself may be subtraumatic. It's
Why are
not
you
going to
pointing
do
at
it.
me?
because I love you and we're going to treat your brain tumor. So 1 beam is subcritical. It doesn't cause damage. 2 beams, 3 beams, 4 beams, 5 beams, 200 beams all coinciding inside the tumor give a lethal dose to the tumor, but don't affect the rest of the brain or the pituitary or lots of other things. So there's gamma radiation is really cool for doing nasty stuff.
Can I just point out that, like, it would have been so easy to pick gamma or X-ray or anything, and we all picked super low frequency stuff because...
And none of y'all picked anything visible, so I couldn't even program it into my costume. Rude.
I'm sorry.
If you programmed gamma into your costume, we'd be worried.
It's how we'll sterilize the room after.
So I want to take a moment to grill Robert a little bit, actually.
Oh.
Yes.
So I would argue that if I were to be holding a pendulum that's swinging back and forth a couple times a second, that is not a wave. That's just an oscillation. A wave has to be traveling. Now, you were talking about you were arguing for electromagnetic waves with a frequency of 4 hertz. And a wavelength of several thousand miles. But your argument was dependent on those waves inside the brain. And I would argue that the brain is so small compared to the wavelength that we're talking about here, that really in the situation that you're arguing for, it's not really behaving like an electromagnetic wave, and thus doesn't necessarily belong on the spectrum. It's really just an electromagnetic oscillation.
Take that.
Ooh, you have obviously never met an electrophysiologist. Because as a matter of fact, we have something that is called ephaptic communication. And actually, I gave a lecture on this one time, and a science fiction author then incorporated it into one of his books, as a matter of fact, and then blamed it all on me. Because with ephaptic connection, what we do know about neurons, how they communicate, is they have electrical activity, they generate their own current, and they then use that current to create ion flow in a sealed tube, basically the axon. And when the action potential reaches the end, because there is actual electron flow and proton movement as well, we then will see that the electrical activity will open reservoirs of a neurotransmitter. That neurotransmitter will pass through over a gap and then activate the next neuron, which, as you rightfully point out, is not an electromagnetic wave. Except that what we now know is that the oscillators in the brain do not communicate via the neurotransmitter system. They actually do communicate via an imposed electromagnetic wave function, which is how the theta is thought to affect other parts of the brain, is through an electromagnetic conduction, because after all, the brain is mostly salt water and fats.
That's awesome.
Hi, hello. It's working? All right. So I wanted to know a little bit more, because I noticed we're talking about radio waves and stuff. We're talking about seeing the rest of the universe. But then the apocryphal story of vaporizing a chicken. What is the purpose of these giant radio telescopes and other devices being able to produce a radio signal instead of being able to receive it? It's not like we're trying to echolocate out to light years away. Why do they have the ability to transmit energy in such high amounts, and what is the purpose of those, and how is it generated?
It's an excellent question. Arecibo is one of the few radio observatories that had transmitting capabilities. Actually, it can be used to probe our Earth's own atmosphere, particularly the ionosphere, the part of our Earth's atmosphere that is, broken up into charged particles. So they can investigate effects of solar weather on the Earth and the Earth's atmosphere, and whether those can get through and do things like mess with all of our electronics. It was also used for making radar maps of the moon, as well as some radar. I think there were some radar studies of the planets in the solar system. So not quite light years, but many miles. Arecibo was. I say was.
Yeah.
Arecibo was a unique instrument and still incredibly important in these particular fields of atmospheric physics and planetary science. And so I am very much in favor of efforts to find a way to bring that capability back.
Mm-hmm.
Excellent question. Thank you.
Last question.
This is for Robert again, but this was more out of curiosity. So you mentioned how a brain, if you measure that frequency and then you make that and the creature hear that same frequency, it bias it, right? If you took it for example, if a creature eventually got Alzheimer's and you had its healthy signal and then you introduced it to it and then it got Alzheimer's and you reintroduced the healthy signal, what would happen?
Well, actually, that is the basis that a number of groups are trying to build neural prosthetics and implants to overcome Alzheimer's by reintroducing a healthy theta rhythm. And beyond that, I can neither confirm nor deny. But no, and I say that jokingly, I can. That is what we're attempting to do in the field of neural prosthetics, is to put back a healthy signal.
Do you work in Parkinson's prostheses?
Not directly.
So, I think you all have heard the arguments for the various parts of the spectrum. So now we are going to do a vote. And I would normally do by applause, but I don't want to go deaf. So, wave your hands over your head as we go down the line. So, who thought the infrared was the spiciest part of the spectrum? Okay, fine. We'll do the shouting thing. Who thought the infrared was the spiciest part of the spectrum? Who liked the M in electromagnetic spectrum? Who thought that radios are the most vaporizingly awesome part of the spectrum? And who wants those brains? I think it's a tie.
Sounded like a tie.
Thank you all for joining us. Please remember to rate us in the app. Please remember to donate to the charity. And if you want more
That means I beat Topher. A year-long argument in the making.
If you still want more science, come join us in Hilton Grand East for the 3 F's of the animal kingdom. Fight, flight, or mate.
Mate.